And Assalamualaikum, my name is Muhammad Hakim bin Zamzlani and my matrix number is DE20100. Today I will present about introduction in our group project. So our introduction is a DC motor is an electric motor that runs on a direct current, which is DC power. It converts electrical energy into mechanical energy through the interaction between a magnetic field and a current carrying conductor, typically a coil wire. DC motor are commonly used in a wide range of applications, including automobiles, industrial machinery, and household appliances. They also can be controlled using various methods, such as varying the current or voltage supply to the motor, or by using electronic controller. DC motor also are widely used in industrial and domestic application due to their wide speed control range, high starting torque, high transient response, and compactness. This means that speed, torque, and even direction of rotation can be changed at any time to suit new condition. The combination of proportional, integral, and derivative control action is called PID control action. So PID is a proportional integral derivative, which is a control loop feedback mechanism that is widely used in industrial control system and other application that require continuously modulate control. PID also continuously calculate an error value as the difference between a desired set point and a measure process variable and applies a correction based on proportional, integral, and derivative term. The proportional term, which is P, provide a control output that is directly proportional to the current error value. The integral term I means provide a control output that is proportional to accumulate error over time. The derivative term, which is D, provide a control output that is proportional to the rate of change of the error. By adjusting this parameter PID of the controller, the system control performance can be optimized. PID controllers are used in a variety of applications such as temperature control and others. So this is we consider the feedback system architecture, which is showing in this figure 3.1 below, where it can be assumed that the plant is a DC motor whose speed must be accurately regulated. So this is the set point, and this is the PID and the process, and go to the output. So PID controller is placed in the forward path, so there is output is the voltage applied to the motor armature. The feedback signal is the speed measured by tachometer. The output velocity signal, which is CT, is assumed with the reference or common signal, which is RT, to form the error signal, which is ET. Finally, the error signal is the input to the PID controller. DC motor have long been popular in the industrial control field due to their many outstanding properties, including high starting torque characteristic, high response, easy linear control. The speed of a DC motor is given the relationship, which is N equal to V minus IR per K. Hi and Assalamualaikum, my name is Muhammad Hakim bin Zamzlani and my matrix number is DE20100. Today I will present about part A, which is mathematical and block diagram derivation. As shown below, this is the table for DC motor data, which is have parameter and value, and the value is given from the equation. So the first equation, which is the Laplace transform of armature circuit equation, is VA, which is rated motor terminal voltage, equal to IAS, which is armature current, multiply with R plus LS plus EBS. So first step is we let that JT equal to JM plus JL. JM is moment of inertia of the rotor. JL is moment of inertia of the load, which is blade. So after that, we also let that BT equal to BM plus BL. BM is motor viscous friction constant and BL is viscous friction of the blade. After that, the first equation we apply to the motor is TMS equal to theta ms multiply with JM plus JL multiply by S power of 2 plus BM plus BL multiply by S. So we get that TMS equal to theta ms JT plus S the power of 2 plus BT multiply by S. After that, we get the relationship between the torque, which is TMS, and the armature current IAS is TMS equal to KA multiply with IAS. So the relationship between motor EMF, which is EBS, and motor shaft velocity, which is omega ms, equal to EBS equal to KBS theta ms. So now we have 4 equation, which is VA plus IAS multiplied with R plus LS plus EBS. So the first equation. So the second equation is TMS equal to theta ms multiplied with JT multiplied with S the power of 2 plus BT multiplied by S. So the third equation is TMS equal to KA multiplied with IAS, and the fourth equation is EBS equal to KBS theta ms. So from that equation, we combine, we put the equation 2 and 3, which is IAS equal to theta ms multiply with JT KA multiply S2 plus BTS, and this is the equation 5. And after that, we insert equation 4 and 5 into equation 1, which is VA equal to IAS multiply with R plus LS plus EBS. We can get that VA equal to omega ms multiply with JT multiply with S the power of 2 plus BT multiply with S over KA. After that, multiply with R plus LS plus KBS theta ms. So we can assume that ZA equal to JT multiply with S power of 2 plus BT multiply with S, and we also multiply the equation with R plus LS. So therefore, the equation will be VA equal to omega theta ms multiply with ZA over KA plus KBS, and it will be theta ms over VA and KA over ZA plus KA KB KS equal to theta ms equal to KA over plus BT S multiply with R plus LS plus KA KBS. We can get that the answer is omega theta ms equal to KA, and after that we can insert the values of the DC motor data into the equation, which is theta ms equal to VAS equal to 1.28 over S the power of 3 times with 0.444 multiply with 0.121 plus S the power of 2 multiply with 0.444 times 11.2 plus 0.0035 multiply with 0.121 plus S multiply with 1.28 multiply with 1.25 plus 0.0035 multiply with 11.2. So the total after we calculate the equation, we can get theta ms over VAS is 1.28 over 0.0537 s power of 3 plus 4.9732 s power of 2 plus 1.6392 power of s. So we can put the answer into the block diagram, which is the input is VES, and go to 1 over LS plus R, and after that go to KA, and after that go to 1 over JTS plus BR, and go that 1 over S. So this is the block diagram for this transfer function.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Nabil Hakim ibn Barisham. Our matrix is DE210055. I would like to present the manual tuning of PID gain. So, first of all, we determine the characteristic equation CE above block. So the characteristic equation is 1 plus KGS HS equals to 1 plus 1.28K divided by 0.0537 s to the power of 3 plus 4.9732 s power of 2 plus 1.6392 s equals to 0. So when we simplify it, it becomes like this. Alright. So by using cross multiply, A equals to 4, we take this value from s power of 3, s power by 2, and s power of 1. So then A equals to 4.9732 times 1.6392 minus 0.0537 times 1.28K divided by 4.9732. So we won't finish the equation, but we will continue by B. So the value of B is, we take value A times 1.28K divided by value A. So our value for B is 1.28K. In order to give the equation a stable condition, first we take the value of A, again back here, A is bigger than 0. Then when we simplify it, we put 4.9732 to the other side, so it becomes 0. Then we simplify it again, we put 8.1521 to the other side. So negative 0.06874K is bigger than negative 8.1521. We simplify again by removing the negative of each sides. And then last but not least, we want the value of K, so we put 0.06874 to the other side. So times when we put it to the side, it becomes divide. So K equals to 1.118.593. Next, the second condition is by 1.28K is bigger than 0. So K is bigger than 0. For stable condition, 0 for K is bigger than 0 but smaller than 1.118.593. The value of critical, K critical or K critical is 118.593. So for K critical, we have in imaginary roots as below. We take the value of 4.9732s power of 2 plus 1.28K. So when we have the value of K critical, we put it in this formula, and then we will get 4.9732 s power of 2 plus 151.7990 equals to 0. First of all, we take 151.7990 to the other side, so it becomes negative. Then times, when we put it to the other side, it becomes divide. So our final answer is s, the power of 2, becomes negative 30.5 5324, but this is not the final answer because this is s power of 2. So when we want s, we put the power of 2 to the other side, it becomes square root. So the square root of 30.5324 equals to plus minus j 5.5256. Next. So the sustained oscillation at the limiting value of K critical is 5.5256 radius per second. That's P critical. Period of oscillation is equal to 2 pi over omega. So the value of pi is 3.142 and the value of omega is 5.5256. So the value of P is 1.137 seconds. So this is our group's PID gain for manual tuning. The first PID type is P, so Kp equals to 0.5 times K critical. Our K critical is 118.593. So 0.5 times K critical is 59.297. Our Ti for PID type P is infinity and Ki is 0. The TD for PID type P is 0 and the KD for PID type P is also 0. So for Pi, our Kp is 0.45 times K critical. Our value is 53.3669. For Ti, our PID type Pi is 1 over 1.2 times P critical. So P critical is 1.137. We just put in this formula and then we will get 0.9. And for our Ki, for PID type Pi is 0.54 K critical divided by P critical. So our value is 56.3239. So for our TD for PID type Pi is 0 and KD is also 0. So for Kp for PID type PIDN, the value is 71.1558 when we put 0.6 times K critical times K critical. For Ti for PID, 0.5 times pi times P critical, we will get 0.5685. And for Ki for PID is 1.2 times K critical divided by P critical. So our answer is 125.1641. And for TD PID, 0.125 times P critical. Our answer is 0.1421. And for KD, for PID, our answer is 10.113. That's all for PID gaining.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqmal Fitri bin Farizal. My matrix number is DE210110. As we can see here, this is a subsystem of DC motor in the MATLAB. We already designed right here. Then after that, we continue to the block diagram of system in the MATLAB using step, using subsystem, using bus, and using scope. After that we run. Before that, we should setting the step, which is the RPM. The final value is 1500, and then we can go to the scope to see the graph. The graph will execute.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Farah Ain binti Nurhan. My matrix number is DE210088. So I will explain on part D, which is to implement P, PI and also PID controller using PID gain from table 1. So this is the table 1. Okay, so from here we will insert the value of P, PI and also PID. Okay, so we will insert this value of gain into this block diagram. Okay, so explaining the block diagram, I'm using Simulink from MATLAB. So in order to boot all of this circuit, we can use library browser in the MATLAB. From here we can see in the Simulink there is also blocks that is commonly used. So we can insert gain, integrator and also scope. So this one is summing junction. So this is the components that we use for Simulink. So we will also use subsystem. Okay, so this subsystem is obtained by the mathematical modeling and also transfer function that we have obtained before. Okay, from this one, we can see that this is the block diagram of the transfer function. So from this block diagram, we created a subsystem. So from here, we can see that there is value of JT and also R and also KA. Okay, so we inserted the DC motor data into this block diagram of transfer function. Okay, so this is all the information we collected from the DC motor data. Okay, so now that we have covered the subsystem, this is the overall block diagram that we will use. So here we can see that there is 3 scopes. So this 3 scope will be used to display the output of proportional controller, PI controller, and also PID controller. Okay, so for the first one, okay, so this is the first one that we gain from running the simulation. So I will press the running simulation. Okay, so we can see here that there will be 3 results. Okay, so let us try the PID. Okay, we try the PID. Okay, so this is the result that we obtained from the PID. Then we can see by using the trace selection, we can see the peak to peak. So we can use all of these tools in order to help us to find the information we needed. Okay, so this one is for the PI. Okay, so all of these readings are very different, and it is very important for us to firstly understand how this whole control system works. Okay, that explained for part D.
Okay, we go to the next simulation, which is auto tuning. As you can see here, we're using step, sum, PID controller, bus, and scope. For that, we should set the step value, which is final value is 1500 RPM. After that, we should set the PID controller. We should change the select tuning method to transfer function based PID app tuner. Then we tune. Then we'll execute a graph. After execute a graph, we should, as you can see here, the parameter. You can see the parameter. The parameter here is 10.1. As the requirement in the question, they need the overshoot is less than 10. Then we setting the graph. After we setting the graph, the overshoot is less than 10. This overshoot should less than 10 because if there is a higher overshoot, the accuracy will be low.
For now, this is the comparison of manual and automatic PID controller. As you can see in our figure, this is the block diagram of PID manual. Then, compared to our automatic, this is the figure of a block diagram of automatic PID tuning. We can see the difference between manual and automatic circuit block diagram. Next. So this is our comparison of input speed 1500 RPM, manual and automatic response. These are the three line for our 1500 RPM for automatic and manual response. This is our figure for manual parameter from PID tuning. As we can see in the graph, our peak amplitude is 1.06, overshoot 5.91, all time in seconds 0.25. So the rise time is 0.0823, and then continuing to the setting time of 0.086. Finally, our final value is 1. So this is our manual parameter from PID tuning. Now is automatic parameter from PID tuning. So from the start, we can see that the subsystem from rise time is 0.0793. It rises until time 0.243. Overshoot is 8.1%. The peak amplitude is 1.08. So continuing to second 0.642. Finally, the final value is 1. So what we can see is both the automatic and manual tuning PID controllers produce results with a very similar step response. Automatic tuning has a 3 millisecond faster rising time than manual tuning. In contrast to automatic tuning, which overshoots by 8.1% at 0.243 seconds, manual tuning overshoots by 5.91% at 0.25 seconds. Automatic tuning is 0.218 seconds faster than the manual tuning for the settling time. The final value of both manual and automatic tunings remains the same. It is 1. So this is our PID tuning, manual and automatic. OS percent is for manual 5.91% and for automatic 8.1%. Our TP for manual is 1.06 seconds and automatic is 1.08 seconds. Our TR is 0.0823 seconds and automatic is 0.0793 seconds. So our TS is 0.86 seconds and for manual, and for automatic is 0.642 seconds. So both are these PID tuning, manual and automatic, is stable. That's all for comparison of manual and automatic PID controller. Thank you.
Okay, next for the conclusion. PID controller is a widely used control loop feedback mechanism that is capable of continuously modulating control in industrial control system and other applications. It is also used proportional, integral and derivative system to calculate and apply correction to the control output based on the error between the desired set point and the measured process variable. And a DC motor is an electric motor that runs on direct current power, converting electrical energy into mechanical energy through the interaction between a magnetic field and a current carrying conductor. PID controller can be used to control the speed and position of DC motor by continuously adjusting the applied voltage or current to the motor. By carefully turning the PID controller parameter, the DC motor performance can be optimized for a specific application. Together, a PID controller and a DC motor can form a powerful and reliable control system for a variety of industrial and commercial applications. That's all from me. Thank you.